First of all, one interesting comparison I'll put before you. Magnet, full name is magnetic dipole, and the most common name is magnet itself. With electric dipole, you always use the complete name electric dipole. You see, P stands for letter P. It stands for electric dipole moment. For electric dipole, this is called electric dipole moment. But normally what's common, you see, electric dipole moment, you never use the term electric. It's most common. P is always read as dipole moment. Whereas this magnetic dipole moment, we'll study right now, its complete name is magnetic dipole moment. But what is most common here is magnetic moment. We never use the term dipole here. So, this differentiation must be clear in your mind. Complete name for both is electric dipole moment and magnetic dipole moment. Commonly used here is dipole moment, and that here is known as magnetic moment. We are going to emphasize magnet and magnetic moment. How do we measure magnetic moment? First of all, it's a vector quantity. Its direction is always from south to north inside the magnet, and this is from north to south outside the magnet. Actual length, one border to another, that's actual length. But you see, the magnetic poles are always a little distance inside, not exactly at the corner. They are always shifted a little distance inside. That's why the line joining the two poles, that's known as magnetic axis, and the distance between the two poles is known as magnetic length. Magnetic length is going to be always less than actual length. That is almost 84% in most of the cases. That's about 84% of the actual length. Magnetic moment is given as the product of pole strength and total length of the magnet. But here you should be alert. We have to use only the magnetic length. Suppose a bar magnet is given this shape, U shape. Then the distance between the two poles, this is going to be the magnetic length, as here. This is going to be the magnetic length. Once you say that magnetic moment is a vector, obviously when two magnets or more than two magnets are arranged in different ways, then in order to find the resultant magnetic moment, what you have to do, you have to find the vector sum of all the magnetic moments. For example, suppose you are having two magnets here. Now these two magnets are in opposite direction. If the two are in opposite direction, south, north, north, south. They are arranged but in opposite direction. So, in that case, you will take the difference of two magnetic moments. This is going to be the resultant. But had they been in the same direction, means north above the north, in that case, what you will do, you will find the sum of the two magnetic moments. Similarly, if two magnets are arranged in such a way that the angle between them is going to be theta, then you will apply the vector method to find the resultant m1 square plus m2 square plus 2m1 m2 cos theta. One more thing, you see, if you could interestingly make a triangle with the help of three magnets in cyclic order, then the net magnetic moment is going to be zero. Although you'll be having their three magnets, but even then the total magnetic moment will be equal to zero. But simply when you say cyclic order, then in that case what you have to do, you have to maintain the order of this arrangement, means south to north, south to north, south to north. Then if you cut a magnet in two equal parts, either along the length or perpendicular to length, in both the cases you are going to have each part with half of the magnetic moment. I'll illustrate one by example. Suppose this is the magnet and you have cut it into two equal parts. Now, new magnetic moment is going to be pole strength hasn't changed. Only the length of the magnet has changed. For one part, you are going to have this thing that is m by 2. And suppose you just cut the magnet along the length in two equal parts. In that case, you are going to have, now the pole has been cut in two parts. The area has gone to half. That's why the pole strength has become half, but the length is unchanged. In that case, you are going to have the magnetic moment again half of the actual value. Now, in the last, I am going to give you one very interesting example that a bar magnet is given the shape of letter U, or you might say half circle. It is better to say half circle. Half circle, that means the length that initially was L now has become pi r. And the two poles, now they are at a distance of diameter which is equal to 2r from each other. Obviously, it's going to be the magnetic length. So, new magnetic moment is going to be pole strength into the magnetic length, and that is going to be 2r. M2 into 2. In place of r, you would write L upon pi. You see, m into L, that is capital M, initial magnetic moment. This is the new magnetic moment. So, if a bar magnet is given the shape of half circle, it is going to have new magnetic moment that will exactly 2 upon pi times the initial value. That way you could give any shape and that will change the magnetic moment accordingly.